All right, it says using similar triangles, we're going to write as many proportions as we can for this triangle, or for these triangles. So if I look at this large triangle and this small triangle here, both of them have a right angle, and they also share this angle in common. So that by AA, they're similar triangles. On my large triangle, the side that's in between my 1 tick mark and my right angle is side B. On my blue triangle, the side that's between my 1 tick mark and my right angle is side Y. That would be equal to, on my big triangle, the side that's between my right angle and my angle with no tick mark is A, over the side between my no tick mark and my right angle on my blue triangle is H. And then we have another one last side here, one last side. So on my big triangle, the side that's across from my right angle is side C. And on my blue triangle, the side that's across from my right angle is side B. So using these three things equal to one another, we can actually write 3 separate proportions here. We can write B over Y is equal to A over H. We can write B over Y is equal to C over B. We can also write A over H is equal to C over B. Okay, so now using the big triangle again, and this triangle here, both these triangles have a right angle, and these triangles share this angle in common. So we can write some ratios based off of this. So I can write the side in between the right angle and the angle that has 1 tick mark on it, or 1 arc, on my big triangle is A, over, on my blue triangle, the side in between my right angle and my 1 arc is X. That would equal the side in between my right angle and the angle that doesn't have an arc on it. On my big triangle is B. On my blue triangle it's H. And then the side across from my right angle on my big triangle is C. All over the side across from my right angle on my blue triangle is A. So out of these 3 ratios, I can actually write 3 different proportions. I can write A over X is equal to B over H. I can write A over X is equal to C over A. And I can write B over H is equal to C over A. And then, with that information, since I know that this triangle is similar to my big triangle, and this triangle is similar to my big triangle, and I can say these triangles are similar to each other. But on these triangles here, A is not congruent to angle B. Instead, angle A on this triangle angle A, remember, was congruent to angle A on my big triangle, and angle B was congruent to angle B on my big triangle as well. So those are not congruent to each other. Instead, angle A on my red triangle is congruent to this angle here on my blue, and angle B on my blue is congruent to this angle here on my red. So with that information, we can now create 3 more ratios. So the side in between my one arc and the right angle is y. On my blue triangle, that would be over h. Then, on my red triangle, the side in between my right angle and my 2 tick marks is h. Over on my blue triangle, that would be x. And then, lastly, the side across from my right angle on my red triangle is b. Over on my blue triangle is a. So I can write 3 more ratios with these, or 3 more proportions with these 3 ratios. I have y over h is equal to h over x. I can also write y over h is equal to b over a, and I can write h over x is equal to b over a. And then also I can also flip all of these fractions around to create even more proportions, but I'm not going to do that. We're going to stop there. So we are going to be proving the Pythagorean theorem now using what we just talked about, using similar triangles. There are so many different ways to prove the Pythagorean theorem, but since we're learning about similar triangles, I thought that we should learn how to prove the Pythagorean theorem using similar triangles. We are actually going to be using these 2 proportions in our proof, and we're using this figure up here, and we want to prove that a squared, which is a leg squared, plus b squared, which is another leg squared, equals c squared, our hypotenuse squared, on this giant right triangle. That's what we're trying to prove. Now on this figure, we're given that CD is the altitude of triangle ABC. That's all we're given. So that's the very first step in your proof. Now I just showed you that triangle ADC was similar to triangle CBD, and it was similar to triangle ABC. So we're gonna, or ACB, sorry. So we're gonna write that as well. That's by AA similarity. If we know that these triangles are similar, we created similarity proportions up here. We're only going to use these 2 because that's going to help aid in the proof. But we can say that b over y is equal to c over b, and they wrote this a little bit differently. They wrote it as a over c is equal to x over a. You can write it like that, or you can write it how I wrote it. Actually, let's just write it how I wrote it. So I'm just going to write it differently now. I'm going to just, it's maybe a little easier to see too if I write it like this. B over y is equal to c over b, and a over x is equal to c over a. That's similar triangle rules. All right, so then we're going to use the cross products property. When I use the cross products property here, an a times an a is an a squared, and then I have a c times an x. When I do this one, a b times a b is a b squared, and then I have a c times a y. So using the cross products property, I have an ax squared equals cx, and I also have a b squared is equal to cy. Now what we're going to do is we're going to add these two equations together. So if I add these two equations together, I'll do it over here. We just wind up with an a squared plus a b squared on the left side of the equation, and that equals a cx plus a cy on the right side of the equation. So that's just addition. I added the two equations together. Now we should notice that over here, both of these terms have a c in them. So we can use the greatest common factor to factor that c out to get an a squared plus b squared is equal to c times the quantity x plus y. Well, if we look at our figure up here, x plus y equals c. That's the segment addition postulate. So x plus y equals c, that's the segment addition postulate. So if I know an x plus y equals c, I can take this c and I can substitute it in for this x plus y here. So I wind up with a squared plus b squared equals c times c. That was substitution. And now simplifying a c times a c, you get a c squared. I just proved the Pythagorean theorem. A squared plus b squared equals c squared. All right, that brings us to the end of this lesson.